Hello everyone, I am Abhishek Datta and you all are watching my YouTube channel Mathematics Made Easy. Today in this video I am going to discuss some more theories and concepts about matrices. In my previous video about the theory of a matrix, I have discussed the very basic concept of a matrix, by the order of a matrix, what information we have when the order of a matrix is known. Also I discussed about the types of some particular matrices such as a row matrix, a column matrix, a square matrix, a rectangular matrix, and also a little bit concept about a symmetric matrix. And in the later part of the video we discussed about a particular operation on a matrix known as the transpose operation. Now in this video let me take the discussion in more details by showing you how to represent a matrix by positioning its elements in the coordinate structure, in the coordinate form. Now this particular representation, that is to represent a matrix by positioning its elements in terms of coordinates, has a huge application in the study of networks and also in computer sciences. Let me illustrate with an example and let me deal with a matrix of order 2 by 3, that is a matrix having 2 rows and 3 columns. So let us consider a matrix here, say capital A, a 2 by 3 matrix whose elements are say 2, -1, 5, 7, 8, 9. So here we have a 2 by 3 matrix A. These are the elements 2, -1, 5, 7, 8 and 9. Now how to represent these elements by the coordinate system form? To do so, we represent every element of this matrix by A with two suffix I and J. This is the form of representation. Each and every element is represented by a lowercase letter a. We can use any other letter also, but since the matrix is named as capital A, we are representing the elements as the corresponding lowercase letter a with two suffixes I and J, where the left suffix I corresponds the row position of this particular element and the right suffix j corresponds the column position of this particular element. So this is the row position, the row suffix. This gives us the row position and j gives us the column position of this particular element. That means for the elements in the first row, we have the 3 elements in the first row. So for each of them, their left suffix, that is the row suffix, should all be 1 because all of them belongs to the first row. So their left suffixes are all 1 and their right suffixes should vary as 1, 2 and 3 because they respectively belong to first column, second column and third column. So the right suffix j represents the column position, the column suffix. So for this element it belongs to the first column, so the right suffix is 1. This is the element belonging to second column, so its right suffix is 2. And this element belongs to the third column, so its right suffix is 3. That is, the elements in the first row are respectively denoted by A11, A12 and A13. So here A11 stands for 2, A12 stands for -1 and A13 is given by 5. Similarly, for these elements in the second row, for each of them, their left suffixes should all be 2, that is, the row suffixes are all 2 and their column suffixes being 1, 2 and 3. So here A21 stands for 7, A22 is 8 and A23 is 9. So this is how we can represent the elements of a matrix by assigning a coordinate position to each of them. Similarly, for a square matrix of order 3, if we have a matrix of order 3 by 3, a square matrix, here we have a rectangular matrix. For a square matrix, we have 3 elements in the first row. For each of them, their row suffix should be 1. Column suffixes are 1, 2 and 3 respectively. For the elements in second row, their row suffixes, that is left suffixes, are all 2 and the column suffixes vary as 1, 2 and 3. And similarly for the elements in the third row, their left that is row suffix are 3 and column suffixes varies as 1, 2 and 3. So this is the representation of a third order matrix, that is a 3 by 3 matrix, by assigning coordinate position to each and every elements. Now in this coordinate positioning form, you see there are some elements like A11, A22, A33, these elements. For these three elements, their I and j suffixes are equal, they are the same. So such elements Aij, for which I and j are same, are known as the diagonal elements. So these are the diagonal elements of the matrix. That is the elements Aij, which belong to the same row as well as the same column. So this one belongs to first row as well as first column. This element belongs to second row as well as the second column. And this one belongs to the third row as well as the third column. So these are the diagonal elements of this matrix. And the remaining elements where I and j are not equal, these are the non-diagonal elements. Likewise, in the previous example also, we have A11 and A22 as our diagonal elements, and these are the non-diagonal elements. And if you join these diagonal elements by a line, then this is known as the principal diagonal of this matrix. So by the diagonal of a matrix or the principal diagonal of a matrix, we shall mean the line formed by joining the diagonal elements. Now there is a slight difference in the concept of a diagonal in case of a matrix and in our normal geometry. In geometry, a diagonal always starts from one corner and extends to the other corner, whereas in case of a matrix it may not be so. As you can see in these two different examples, if the matrix is of a square shape, then only the diagonal will extend from one corner to the other corner. Otherwise, if it is a rectangular matrix, here the diagonal starts from the upper left corner, but it is not extended towards the lower right corner, because A23 is not the diagonal element. These are the two diagonal elements. So there is a slight difference in the concept of a diagonal. This is not exactly the diagonal as we know in our geometry. Also in geometry we have two diagonal, two way, for a rectangle or for a square. This is also a diagonal. Whereas in case of a matrix, we cannot consider this line as the diagonal. Why? Because these are the non-diagonal elements. They are not the diagonal elements. By definition, diagonal means a line joining the diagonal elements only. So a matrix has only one principal diagonal formed by joining its diagonal elements. So this is how we can represent any matrix, by assigning coordinate position to each and every elements. Now conversely, we may represent a matrix in a very compact form if we can assign a function to each and every elements. Let me illustrate with an example. Say now we have a matrix capital A given by elements Aij of order 2 by 3, where Aij is defined as a function of I and j, say I plus j whole square. So we can represent any matrix of any order, however large the order may be, in a compact form by assigning a functional relation among the suffixes of the elements. So likewise, if we have to represent this matrix in details, so first the matrix is of order 2 by 3. So we assign the elements in coordinate structure form, that is for the first row elements as we discussed earlier. The left suffixes are all 1, that is the row suffix. Column suffixes are 1, 2, 3, and for the second row elements, their row suffixes are 2 and column suffixes are 1, 2, 3. Now we can simplify each and every element by this functional relation. Likewise for A11, both the suffixes I and j takes the value 1. So the rule is I plus j whole square, which becomes 1 plus 1 whole square, which is 4. Likewise A12 is given by 1 plus 2 whole square, because here the left suffix I is 1, the right suffix j is 2. So just put the values here, 1 plus 2 whole square, which is 9. And similarly we can find A13, which is 1 plus 3 whole square equal to 16. A21, that is 2 plus 1 whole square equal to 9. A22, that is 2 plus 2 whole square, that is 16. And finally A23, which is 2 plus 3 whole square, that is equal to 25. So finally the matrix is given by 4, 9, 16, 9, 16 and 25. So this is how we can represent a matrix of any order in a very compact form, in a very concise form, if we can represent their elements in a functional form. The function should be in terms of their row suffix and column suffix. Next, let me discuss about two particular types of matrices, that is a symmetric matrix and a skew symmetric matrix. I have already discussed about a symmetric matrix in my previous video, but let me now take the discussion in more detail in terms of the coordinate positioning form. So what we discussed earlier, by a symmetric matrix, we mean a square matrix. First of all, the matrix should be a square matrix, capital X, whose transpose coincides with itself. Transpose means if you interchange the rows and columns, the matrix will be exactly the same. A square matrix whose transpose operation gives back the matrix itself is said to be a symmetric matrix. So for example, let us consider matrix X as say 1, 2, 3, then 2, 4, 9 and 3, 9, 7. So here we have a square matrix of order 3 by 3, and if you form X transpose, that is if I make the first row as first column 1, 2, 3, the second row as second column and the third row as third column. So as you can see here, there is no difference between X and X dash, they are exactly the same. So such a matrix X, a square matrix whose transpose gives back the matrix itself, that is X dash is equal to X, such a matrix is said to be a symmetric matrix. And for such a symmetric matrix, we have a very important property about the positioning coordinate of these elements, that is given by Aij, that is the element belonging to ith row and jth column, shall always be equal to Aj, that is the element belongs to jth row and ith column. As you can see the symmetry here, that is for A12, for the matrix X, this is A12, that is the element belonging to first row and second column. So which is same as A21, if we interchange the suffix, that is the element belonging to second row and first column. So this is second row and first column, so this is the common element 2, so they are same. Also A13, that is the element belonging to first row and third column, is same as A31, that is the element belonging to third row and first column. Here we have first row third column element, that is 3, and again third row first column element, again 3. So this property holds for every position element for a symmetric matrix, that the ijth element should always be equal to the jith element, and therefore we can always have a reflection along the principal diagonal of the matrix. As you can see here, that these elements are equidistant from each other along the diagonal, as if we have a reflection. That means if you put a mirror along the diagonal line, you know that in the reflection rule, the object and image are always equidistant from the mirror. So as if we have a reflection along the principal diagonal for a symmetric matrix. And similarly for a skew symmetric matrix, the concept is almost similar. The only difference is a square matrix X whose transpose will be minus of itself. If X transpose becomes negative of itself, then the matrix is said to be a skew symmetric matrix. So as for example, if I now consider a matrix X such that its transpose becomes negative of itself. So say a matrix X is given by 0, 1, 2, minus 1, 0, 3, minus 2, minus 3, 0. So here again we have a square matrix of order 3 by 3. And if I consider X transpose now, so we make the first row as first column, the second row as second column, and the third row as third column. So as you can see here, X transpose is negative of X, minus of X. By minus x we shall mean to multiply x by the scalar minus 1. I have discussed about the scalar multiple of a matrix in my previous video. That is to multiply a matrix by a particular scalar, that is a constant, a number. We have to multiply each and every element by that corresponding scalar. So minus x means we have to multiply every element of x by minus 1, thus by changing their corresponding signs. So as you can see here, these positive elements 1, 2 becomes negative here, and these 3 negative elements becomes positive, the positive 3 becomes negative. So we have x transpose is exactly minus of x. Such a matrix is said to be a skew symmetric matrix, and for such a matrix we have Aij, the ijth element shall always be equal to minus of the jith element. Aij should be equal to minus of Agi. As you can see here, A12, the first row second column element, first row and second column element is 1, and if you find this is 1, and if I find A21, that is the second row and first column element, so this is minus 1. So they are exactly negative of each other. Also A13, that is the first row third column element is 2, and if you now find A31, that is the third row and first column element, which is minus 2. So they are exactly negative of each other. And because of such a property that Aij is equal to minus of Aj, what happens for the diagonal elements in particular, as we know that for a diagonal element I and j suffixes are equal, they are same. So if I now replace j by I for diagonal elements, if I replace j by I, so this gives us Aii is equal to minus of Aii, which implies 2 times Aii. If I shift this negative term on the left hand side, 2 times Aii becomes 0, or which implies Aii is equal to 0. That is, for a skew symmetric matrix, every diagonal elements must be 0. That is a very important point to note. For a skew symmetric matrix, each and every diagonal elements must be 0 because of this criteria. So this is a short discussion about representing a matrix by the coordinate positioning form, by representing the elements in the coordinate positioning form, and about the symmetric and skew symmetric matrices. In my next video, I shall be discussing about the operations, some operations on matrices, that is matrix algebra, how to add, subtract and multiply two matrices, and also some theory regarding these operations. I hope this video is helpful to you. If you have any doubts or queries, you can ask me in the comment section. And if you like my videos, please subscribe to my channel. This will help my channel to grow. Thank you all for watching. Have a nice day.